In our last video, we were introduced to the law of sines, and coming soon, we're going to take a look at the law of cosines. We've got one more little bit of law of sines here and a kind of a mishmash of some other ideas. So in our last video, what we saw is that it's possible that we could create one or even two different triangles if we don't know the third angle. So our problem was if we only have a single angle here, we don't know either of these. And so when we set up now you would need the opposite side. So the law of sines requires that complete ratio. But if you had it and only had one angle, maybe there's two different triangles that exist. Maybe we have one that looks like this, or perhaps one that looks like this. So what we had to do is we checked that value of beta. So suppose we found beta here. We checked it twice. There was a first quadrant value for beta, and then there was also a second quadrant value of beta that we had to double check. Now sometimes that second value would be able to create an entire triangle, in which case we would have two complete triangles. But sometimes that second value of beta, we were calling it beta prime, couldn't possibly exist because it was too large and wouldn't leave any angle left for the third angle in the triangle. Well, there is one other possibility. So anytime we only have the one angle here, we've got some real issues. But we could also have the possibility that the information they gave us doesn't make any sense at all. It doesn't create any triangles. So here they've told us that we have an angle 50 and an opposite side of 4. So that gives us this ratio. So we can set up the law of sines. There's a second side that is 10. So we're looking for the value of this second angle. Well, if I solve that, here's what I get. I get the sine of alpha equals 1.915. That's too big. Sine is limited between -1 and 1, so I can't have 1.915. And so if you tried to inverse this on your calculator, you'd get an error because it's too big. There is no angle that has a sine ratio of 1.915. It's too large. And so what's actually happening here is the information they've given us doesn't create a real triangle at all. This side is too short to go with an angle of 50 degrees. That's impossible. It wouldn't leave enough room to connect with this other side being 10. So the dimensions just don't work. So what we've seen is that you could have 1, 2, or even sometimes 0 possible triangles because it just doesn't work out. Now, here's a slightly different question than what we saw before. This is only asking us to determine how many triangles would be created. So are we going to get 0? Are we going to get 1? Are we going to get 2? So we do have a complete ratio, so let's start to investigate. I've got sine of 48 over 26. I've got sine of alpha over 31. And now let's solve this. So I think I have the numbers here. No, I don't. Okay, so I'm going to do sine of 48 divided by 26. Now I'm just going to go ahead and multiply it by 31. So I'm going to get sine of alpha equals 0.886. I just did all the algebra. Did the side multiplied by 31. Now let's inverse sine that, and let's see what we get. I get an angle equal to 62.38. Okay. Now, we only had one angle, so we have to check. So far, there's at least one triangle. This does work. Let's check. So we're not saying 0. But this value of sine that we've gotten was a first quadrant value. So let's use 62.38 as a reference angle and say, hey, what would the value of sine been in quadrant 2? Because sine is also positive in quadrant 2. So we need 62.38 here. So what we always do is 180 minus 62.38. And I get 117.62. Okay, so possibly there exists a second triangle with 117.62 as alpha. Now, the way we're going to check that is we know beta is 48. Let's see if this adds up and leaves anything in it, and it's going to. Do you see that we're going to have some room left? If I add those two together, I get 165.62. So gamma prime would have to be 180 minus 165.62. These two added up are 165.62. Is there any room for a third angle? There is. I've got 14.38 degrees left. Okay, so that is true. So this could happen. So we actually have decided we have two possible triangles. So one more time through this real quickly. I set up the ratio, I solved for alpha, I got 62.38. So that was possible. So there is one real triangle at least. So it's not like the last one where it couldn't possibly exist. Okay, then I checked using this as a reference angle to say, well, what about quadrant 2 that our calculator didn't give us? In quadrant 2, you'd also get a sine of 0.886 with 117. So I then came over here and checked it. This angle plus the beta, added them up, and there was room left over for that third angle. So this one, it could exist as well. So we settled on 2. Okay, now what we've got here is a different version. You know the area of a triangle is 1/2 the base times the height. Well, if we're in an oblique triangle, the height is not easy to find. So what we're going to do is use our trig tools here to create a couple of formulas. So what we're going to see, if we looked right here, if I extend this altitude down and I'm looking for this height, couldn't we just do the sine of alpha equals opposite over hypotenuse? This should be an equal sign. So couldn't I solve for the height? And height is then c sine of alpha. Okay, so I'm going to take the good old-fashioned triangle formula and I'm going to replace height with c sine of alpha. Now the base here is side B. Do you see how we're sitting on side B? So base is B, and the height, we've just used our basic trig definitions to see that it's c sine of alpha. Now that's the pretty straightforward one. They did the same idea here with an obtuse triangle where the height would be on the outside. It changes things quite a bit, and I was having trouble finding out. They've done some geometry trick to make these other formulas here quite easy. What I did was I started with this one, 1/2 base sine, or c sine of alpha, and I used the law of sines. So I know that sine of alpha over A is equal to the sine of gamma over C. Isn't that what the law of sines says? So I just solved this by moving the A up here. And so I know this is true. So in this formula, which I did understand because it came from this triangle here, this one made plenty of sense to me. I just replaced sine of alpha here with this, A sine of y over C. Did some canceling and it creates the second formula. And then you could use the other part of the law of sines to create the third. So again, they're doing some trickery here with geometry that I'm not familiar with. I don't know very much about geometry at all. But so they did a trick here to make this easy. But I used the law of sines to prove these other two formulas. And it's just a simple substitution and some algebra. But regardless, here's what we get. We get these three versions to find the area of a triangle. You can use any of these and you'll still get there. So notice what happens here is we have the two sides and the other angle. That's always what we need, the two sides and the other angle, and we can find it. So it really is plug and chug once we establish that. I've got the two sides and the other angle. So all I have to do to find the area is drop those in and crunch it, and there we go. So let's try again. So the area of an obtuse triangle, we've got 1/2. I've got the other two sides, and I have the angle. So this is going to be easy. And I've got the sine of 42 degrees. So I'm just going to crunch this. Sine of 42 times 3.4 times 7.2 times 0.5. And I get an area of 8.19. So remember, areas in squared units, so feet squared. All right, we end here with a couple of applied questions. They're pretty straightforward, I think. We're going to use the law of sines to help us find the height of this airplane. Now, there's some story that didn't really tell us, but we have the picture. This is what they're saying. They want the height here. So the first thing I'm going to do, now I'm going to do it either side, but I have, let's see, I have two of the angles. So let's find this third angle. I think that's how they're going to do it. Yeah, that third angle would have to be 130. So let's go back. So I've got 15, I got 35. That leaves this third angle to be 130. Now why did I need it? Because I need a complete side. If this is 130, or a complete ratio, I have the angle and I have the side across from it. So now I can set up a complete ratio. Sine of 130 over 20 is going to equal, now they're choosing, we're going to look for this side here first. We're going to need that, and I'll explain why in a minute. So we've got the sine of 130 equals, so this is just the law of sines. Here we go. We have sine of 30 over the missing side A. We've just solved that. They're showing the algebra in a little strange way, but we get down here, and here's what we get. That side A here is about 15, so 14.98. Now what has that done for us? Well, now we have this right triangle here. We want to find this height. If we take the sine is opposite over the hypotenuse, which we now have. So height is, or sine is opposite over the hypotenuse, and opposite is the height that we're looking for. Crunch this down, we get 3.88. Okay, let's try another one of these so it makes a little more sense. So I've got the same kind of situation here. They want to know the height of this blimp. Okay, well I don't have that information yet, but the law of sines is going to help me. I know the distance between these 2 points. This third angle is going to have to be 48. Just adding these two up and taking away from 180 tells me that this has to be 48. Okay, well now I have a complete ratio. I've got sine of 48 over 145 equals, let's look for this. You could do it either way, but let's look for this one right here. So we'll call that B, sine of 62 over B. Okay, so I crunched all that down, just basic arithmetic here. I'm going to get side B is 173.12. Send him up, just crunch all your numbers. So this is 173.12. That's the length of that side. Well, what good does that do me? Well, now let's think about this right triangle that's created. And the sine of 70 degrees is going to be equal to the height over that hypotenuse, that 173 that we just found. Okay, if we solve this, we get 162.68 feet, or yards, sorry, yards. So one more time, let me take you through here. I had two angles, so I can easily find the third. That third angle, and that's this side, the 145 between the two of them, that sets up a complete ratio. I've got a complete ratio. Let's find this side of the triangle here. So the law of sines says that sine of 62 over b. Solving that, I get 173.12. Now what good did that do me? I want the height. Well, this creates a right triangle. So the sine of 70 is opposite, which is the height I want, over that hypotenuse of 173. Solving this, I have the height of the blimp. Okay, a lot of miscellaneous stuff there. I hope that makes sense. So the first question was, we're trying to find how many possible triangles could be completed, could actually exist, and for the first time we saw that maybe none could exist. Then we saw an alternative formula for the area of a triangle, and then lastly we did a few application problems using the law of sines.